Good morning, everybody. This is Statistical Computing and Machine Learning. Professor Zabaros is speaking. So the lecture today is Gibbs sampling. That's a very fundamental sampling method that is used either alone or in combination with other methods that we will see in the remaining of the course. So let's see what type of topics we will cover today. First, I will introduce the need for iterative or incremental strategies to address the difficulties that we had with previous methods in high-dimensional distributions. And in the process, I will give you some introduction to what's called Markov chain Monte Carlo, just so we can introduce these incremental methods. And a simple example will follow, which is the autoregressive model. Then we will move directly to Gibbs sampling. I will tell you how we managed to sample one component at a time of a high-dimensional vector. I will give you different versions of the algorithm. We will see a number of examples, and in particular, we will apply the Gibbs sampling on what is called Bayesian variable selection for regression models. So this will be a very important application, so important that actually I will devote a whole lecture, a follow-up lecture on this topic to be sure that the details come out clearly. So the goals for today's lecture will be to understand the fundamentals of Markov chain Monte Carlo, at least as an introduction, familiarize ourselves and learn how to use Gibbs sampling, and then learn how to apply Gibbs sampling to variable selection in a Bayesian regression model. Okay, so we already have discussed that many of the methods that we have seen up to now, for example, the inversion method where we use the CDF or the rejection sampling method or importance sampling, those methods don't work in high-dimensional problems. And the reason they don't work in high-dimensional problems is because we're trying to sample high-dimensional vectors with all the components sampled at once. So what we will see today is a new set of sampling algorithms that go with the name Gibbs sampling that allow us to sample one component at a time, or maybe a group of components at a time. So this fits to the general category of incremental strategies for sampling, and in these strategies, of course, Markov chain Monte Carlo is included, but also sequential Monte Carlo, which is a huge and more modern area of Monte Carlo methods that we will visit in follow-up lectures. Okay, let us see a motivating example. This is a standard example that is being reported practically in most courses and in most textbooks in computational statistics. So for example, this is contained in the textbook by Robert and Casella, and it pertains to failures in a nuclear plant. So let's see what the data we have. We have a nuclear plant that has 10 pumps, and we're recording at given times, which is the third row, the failures of each pump. And we're assuming that these failures, and I indicate this number here as pi, follow a Poisson distribution, which we have seen before. That's the right distribution to use when we count events. So this Poisson distribution, p evaluated at lambda I ti, it gives us the number of failures for the pump I at time up to time ti, where each Poisson distribution is defined with its own parameter lambda I. So for each pump, we have a Poisson distribution that defines the number of failures, and lambda 1, lambda 2, lambda 3 are the corresponding parameters in these Poisson distributions for each of the pumps. So as you can see, we have 10 parameters here that they are not a priori known. Okay, so I will introduce in the follow-up slide another parameter beta, okay, that is going to come through some prior modeling, but the overall number of parameters that I'm going to have in my model will be 11, 10 for the lambdas and 1 for this beta parameter that you will see shortly coming up on the follow-up slide. Now, as a reminder, I am showing to you how the Poisson PDF looks like, right? So remember, the Poisson with parameter lambda is lambda to theta e to the minus lambda. Okay, so this is what we will use in the follow-up slides in writing the likelihood for this particular information that we have received. Okay, so we're going to do some prior modeling, and we're going to introduce a hierarchical prior modeling. So we're going to assume that all the lambda i's follow a gamma distribution with parameters alpha and beta. We're going to fix alpha in the applications that we will discuss today, but we're going to make the parameter beta being shared effectively by all the different pumps in the nuclear plant, and they're being shared because this parameter beta comes from a gamma distribution with given gamma and delta parameters. So again, the lambda I parameter for the Poisson distribution that defines the number of failures for each plant follows a gamma distribution. The parameter alpha is taken given, and the parameter beta follows a gamma distribution with given gamma and delta. So what I'm going to do is I'm going to write down the posterior distribution of all the parameters and beta for our model. And so that's the posterior distribution, Ti and Pi. I remind you, Pi is the number of failures for pump I, is the likelihood, which this is the Poisson distribution for each of the 10 pumps. This is the prior model on lambda I, and this is the prior model on beta that's also a gamma distribution. So what we get is we get a posterior that looks in this complicated form, and obviously you can immediately see that it's not going to be easy to use any of the methods that we have seen up to now to sample from this 11-dimensional posterior distribution. So we're not going to be able to use the inverse CDF method or the accept reject or the important sampling method. So we need something different to be able to sample from the posterior distribution that you see on this slide. And the idea here is, so that things can be clear, we're going to try to sample one parameter at a time. So we're going to sample lambda 1, then lambda 2, eventually lambda 10, and then beta, but in a way that eventually the samples will be samples that are actually coming from the joint posterior distribution that you see on this slide. Okay, so now if you look carefully in the posterior that is given in the first equation, you can immediately see that you can write down the the conditional posterior distributions for each of the lambda i's and for beta, and they, just looking at the form here and comparing notes with the way the gamma distribution looks like, you can immediately see that the lambda I the posterior follows a gamma distribution with parameters Pi plus alpha and Ti plus beta, and then beta, given all the lambdas, follows a gamma distribution with the parameters that you see here. Okay, so again, the idea will be to sample one parameter at a time, and I can tell you right away we're going to be sampling from these conditional distributions, but of course the idea will be that somehow we need to guarantee that these samples we get from these conditional distributions are samples that eventually give us values for the whole parameter that is 11-dimensional that comes from the samples of the joint posterior that you see in the top of this slide. Okay, so even though we sample one component at a time, really our objective is to be sure that eventually those samples will be samples that are coming from the joint posterior. So let me just give you what the algorithm is going to look like. So the algorithm is going to start sampling each of the parameters iteratively. So given all the other parameters and beta, I am going to sample at, let's say, time, and this is fake time, so it's iteration really t plus 1. I am going to sample lambda I from this gamma distribution, which is the conditional, and then I will do this for I equal 1 to 10, and then when I am done, I am going to sample beta given all the values of the lambda parameters, because you notice in the conditional for beta, I need to know what those parameters are. So effectively, what we are achieving with this algorithm is, instead of sampling directly a high dimensional vector, an 11-dimensional vector, we sample 11 times for from distributions that are of dimension 1. Okay? Now you may say, is that computationally expensive? Well, you know, for now it doesn't look to be that complex, because obviously sampling in 11 dimensions will be a much more difficult problem. Sampling in 1 dimension is something rather trivial. So we're going to sample 11 scalar variables from these conditional distributions, and then again the idea is, can we guarantee that those samples are samples that come from the joint posterior distribution? All right, so that's the major question. Are we sampling from the 11-dimensional distribution, the joint distribution that we had before? And then of course the second very important question is, you know, since we iterate, do we have to iterate forever? Do we get, you know, some sort of convergence within a finite number of iterations, or we really have to pull this, you know, to infinity? Now, before we discuss about the specific details for the Gibbs algorithm that we reviewed on the previous slide, let me just say that effectively what we're doing is we're generating a sequence of parameters, values, and I call all of these 11 parameters here as theta t, and this is the values of these parameters at iteration t, and that sequence is a Markov chain. So before we proceed, I need to tell you some very elementary concepts about Markov chains, and then we will come back to apply those concepts in a simple way to our Gibbs sampler and make some arguments as to why the Gibbs sampler actually works and provides us samples that come from the joint posterior distribution. Okay, so let me define a Markov chain, right? So a Markov chain is a chain that is generated with some rule. So, you know, if you have a way to sample, let's say, the state x0, and you have a rule that allows you from x0 to go to x1, from x1 to go to x2, then what you produce is a Markov chain, assuming that the way that you go from one state to another, it only depends on the previous state. That's the Markovian assumption, okay? So what we need to come up with a Markov chain is to define a transition kernel that effectively gives us the probability of xn given xn minus 1. So given that we are at a given state at iteration, you know, n minus 1, what will be the next state xn? What will be the probability of xn? Now I have written the transition kernel here in a much more general form. Instead of simply having the probability of xn given xn minus 1, I have the probability of xn being in a certain domain A, right? And I denote this transition kernel as p of x comma A, or even to be more accurate, I can write this as p of xn minus 1 comma A. In the applications that you will see in the lecture today and follow-up lectures, really we will only assume this transition kernel providing the probability of xn given xn minus 1. So for now, what I want you to know is that this transition kernel, it only requires to know xn minus 1 to know what the probability of xn is going to be. Okay? Now, because this is a kernel, in some lectures that are going to come, rather than denoting this with P, I am going to denote this with capital K, just from the word kernel. Okay? It will be obvious from the discussion that we're referring to one and the same thing. Okay, so we're creating a Markov chain using this rule, and the idea is, of course, we have a target distribution in mind, right? We want to sample from some specific target distribution, and the question is, can we make this sequence of x0, x1, x2 eventually to give us samples from that particular target distribution? So the key ingredient here is, how do we actually select this transition kernel so that the target distribution pi is the invariant distribution of this transition kernel? And of course, eventually we need to compute averages using this Markov chain. So effectively, we would like to be able to approximate, let's say, this expectation with the same averages that we use in standard Monte Carlo. The only difference is here we will need to guarantee that eventually xn are samples coming from the distribution pi. Now that looks, of course, a very complicated thing, because, for example, when we wrote this type of approximations before, we noticed that when we talked about Monte Carlo, that these samples xn are IID samples from the distribution pi. But if you have a rule, this transition kernel that tells you how to go from the state n-1 to the state n, obviously this is going to generate correlated samples, and you wonder, how is that possible that eventually we may be able to write some approximations like that? Well, you will see that with very mild assumptions, we will be able to have approximations that look like this. And not only that, but effectively the samples xn will be samples that are coming out from the target distribution pi. Okay, so we will see what those rules, what those mild requirements are going to be. So let me give you a very simple example, and this is an autoregressive model that has a very simple rule. Given xn minus 1, I generate xn as xn alpha times xn minus 1 plus some Gaussian noise, and I consider the absolute value of alpha to be less than 1, so that eventually this autoregressive model converges to some target distribution. Okay, I am not going to derive it. Actually, the derivation is rather simple. And let me just tell you that the limiting distribution that this autoregressive model converges is the Gaussian that you see here, that has a mean 0 and it has a variance sigma square over 1 minus alpha square. So the idea will be now, can we use this chain to actually sample from this target distribution? Now you may say, if I know the target distribution, I can go and sample directly from this without having to bother about the chain. But the idea here is, let's say we don't really know what this limiting distribution is. We would like to sample from this and find out what is the limiting distribution of this Markov chain. Okay, so we will eventually, in this particular case, expect that when we take samples xn, after some time, these samples will actually be coming from this Gaussian that you see here. Now, I'm going to show you a trivial implementation of this, and there are two ways that you can think of numerically simulating this. One will be to start with multiple initial states x0, and then allow these initial states to progress to x1, x2, x3. So I'm going to have multiple chains, each of them starting from different values of x0, and then I will observe what happens to x0 as it moves to x1, to x2 for each of the chains. And at some given time n, I'm going to take all the samples from all of these chains, create a histogram, and see if that histogram corresponds to this limiting Gaussian distribution that you see here. So that's one way of doing it. The other way to do it would be to literally start with only one initial state, run it, and then start collecting samples from that chain. So maybe use the x1000, x1001, x1002, and then create a histogram of those samples from one chain and see if those xn's are also coming from this limiting distribution. And of course, we will see that that's the case with both approaches. Okay? So in the first example, I'm going to show you 100 independent Markov chains, and I mean independent. We're going to have different initial states that maybe are sampled from some, in this case, uniform distribution, all right? And then I'm going to allow my autoregressive model to proceed. The actual parameters that I'm going to use will be alpha equal 0.4, sigma equal to 5. So let's see what happens. So you can see that, you know, after this is the initial distribution, looks anything but Gaussian because my initial samples are coming from the uniform distribution. This is after step 1, step 2, and then after 100 step, I start getting something that very close looks like a Gaussian. So that's one implementation, and I give you actually an alternative. You're going to have to click the links to see how the two implementations vary, but you see these results here, they look a little bit more clean, and after 100 steps, literally I am on the mark. I can see immediately this target limited distribution where the autoregressive model converges. And again, I remind you that you can repeat this by taking samples from one chain. So you don't have to run 100 independent chains. You take one chain and you take samples from that, you plot the histogram, it will give you similar results as the ones that you saw in the previous slides. Okay, so effectively here we created a Markov chain that converges to some limiting distribution, and that limiting distribution was a Gaussian that we could compute analytically. So we store these samples, and eventually those samples will be used to compute averages like that. And as I discussed before, when you compute these expectations the classical Monte Carlo way, you may wonder why that will work, because the samples, after all, they are not independent. So if you take samples from one chain, you don't anticipate the samples to be independent, but I will discuss the limiting number of assumptions that you will need for actually this to be a very good approximation of the expectation, the way that we have seen with standard Monte Carlo methods. As a matter of fact, you can even establish a central limit theorem like condition for the convergence of this Markov chain, and you can, again, with weak assumptions, you can show that the rate of convergence is 1 over square root of n, and again, even though the samples are not IID the way we have discussed in standard Monte Carlo methods. All right, so let's start progressively discuss what those assumptions that need to be satisfied for this being an approximation of the expectation where the samples come from a Markov chain, and of course establishing some rate of convergence that you have seen in standard Monte Carlo methods, this 1 over square root of n. Okay, so first, we need to be sure that the desired distribution is the invariant distribution of the underlying transition kernel that we use, and that means that this equation needs to be satisfied. So this is the integral of pi of x times the transition kernel from x to y for all x's has to be equal to p of y. So the idea here, you can use your intuition. Once you reach p of x, through the transition kernel for all x's, effectively you will be back to the distribution p of y. Now, we will see that an easy way to satisfy this, that pi is the invariant distribution of the Markov chain, which is this equation, is to satisfy what is called the reversibility or the Tel balance equation, which is given like this, okay? And again, I mixed up here the notation. This is a pi, and this is a pi here as well, okay? And this, you can see exactly why I call this the reversibility, because if I am at state x and I transition to y, then this is the same as the probability of being in Y and transitioning in X. Okay, so moving from A to B gives me the same probability as moving from B to A, and that's what this reversibility condition says. I am not going to prove this now because we will do this in a follow-up lecture, but keep in mind that if this equation, with this being P here, again a typo mistake, if this equation is satisfied, then P is the invariant distribution of the transition kernel P of X and Y. Now we will see that there are many transition kernels that will admit this distribution pi of X as the invariant distribution, and the main task in Markov chain will be to find a good transition kernel. Okay, so we will need to satisfy that. This is one of the conditions that we will need to satisfy, and we need to be sure that the Markov chain converges basically to the distribution pi of X, regardless of what initial states I start. And I can tell you now that, you know, when you start with some initial states x0, you have basically to disregard your samples for some time, and that period that you will disregard your samples is called the burn-in period, and then start taking samples after some time. So maybe in a Markov chain, let's say you get rid of your first 1,000 samples. After that, your samples are good, and they are coming from this target distribution pi of X. But somehow we need to be sure that we always converge the pi regardless of where we start. Now, and again, the idea will be that somehow we need to be generating samples through the Markov chain so that this sample mean converges to the true expectation of F under pi, and in the strongest case, of course, guarantee that Xn are samples that are coming, they are samples coming from the distribution pi. Okay, there are two additional conditions that need to be satisfied, and I'm going to give you a description of them with simple words and examples in the lecture today, and there will be more details coming in follow-up lectures, but those additional conditions go with the names irreducibility and aperiodicity. So let me say with words what this irreducibility condition is. You need to guarantee that if you start from any location X, that there is a finite probability that you can transition to any location Y, all right, with a non-zero probability. So if I am at X, the probability of transitioning to Y has to be non-zero for any Y. That's what irreducibility means. So you need to be able to guarantee that you can sample all the support space, right? You can move everywhere from any location. And that's the condition of irreducibility. Now, the second condition is, if I can go back, the second condition is this aperiodicity. Means as you move from one location, from one state to another, you need to be sure that you are not periodic in the way you sample the different states. So if you start at a given location, you need to guarantee that there will not be a finite time that you will return to the same location again and again. So you can not allow that, let's say after 5 iterations or 5 time steps, you're always back to the same state. And this is what I call aperiodicity. So now when those conditions are satisfied, then indeed you can approximate your true expectations with the sample mean, even though your samples are not IID. You can guarantee that Xn are samples coming from your target distribution, and effectively you can guarantee that the rates of convergence will be similar to what we have seen for standard Monte Carlo methods. Now, of course, in this type of problems with Markov chains, to establish the actual rate of convergence is way much more difficult than what we have seen in standard Monte Carlo methods, and I am not in this course going to show you any proofs that relate to this matter. Okay, so let's go back to the Gibbs sampling, right? So the Gibbs sampling effectively works because we are generating a Markov chain, and under some weak conditions, we're satisfying this irreducibility and aperiodicity conditions. So eventually we converge to the target distribution. Now, I haven't said to you yet what the transition kernel is in Gibbs sampling. The only thing that I told you is that I sample one component of my high dimension vector at a time using the conditional distributions. But if you wait for 1 or 2 slides, I'm going to show you what is the corresponding transition kernel that allows me to go from one state to the next. So let me summarize the algorithm, and I'm going to do this for a distribution pi of theta that has 2 components, theta 1 and theta 2. So we're going to start by some initial state that you can sample it completely randomly. It can be anything. And then for iteration I, you sample the component theta 1, where you keep the value of theta 2 fixed to the previous iteration, whatever you had at the previous iteration. And then you sample theta 2, where now you notice the conditioning uses the sample theta 1 that you just sample on step 1. Okay? So these are the 2 conditionals, and yes, and again, pay attention that the conditioning, you have to use the most updated information for the parameters that you condition on. All right, so in this case, you condition theta 2, so the only parameters you can use are from step I minus 1. Here you condition on theta 1, so the parameters that you can use is the theta 1 that was sampled in step 1 of the algorithm. So this creates a Markov chain, and so I need to tell you now what the transition kernel is, so that you know, this can fit in this general category of Markov chains that we have seen. So here's what the transition kernel is. Remember, the transition kernel requires to know where you are and where you're going. Okay, so that's the probability being at theta 1, theta 2, and transitioning to theta 1 tilde and theta 2 tilde. And based on the rules that we use to sample from the conditional distributions, you can immediately extrapolate that the transition kernel is nothing else but the product of these 2 conditional distributions. The first one is P of tilde of theta 1 given theta 2, and the second one is P of tilde of theta 2 given theta tilde of 1, which we just sample. Now, you may say, well, you know, that's fine, but can we actually show that the distribution pi of theta 1 and theta 2, it's actually the invariant distribution of this transition kernel? Well, yeah, we can show that. So we can prove this equation, and the proof is rather simple. So what I'm going to do is I'm going to start with the left-hand side. So x here is theta 1, theta 2, y is tilde of theta 1, tilde of theta 2. So I am going to plug in what my transition kernel is. This is what I have. This is what I have. And now notice, here I have pi of theta 1, theta 2, d theta 1. So actually I can marginalize. There's no theta 1 coming anywhere else. So I can get rid of theta 1, and this becomes the marginal of theta 2. And then the marginal of theta 2 times this conditional of tilde of theta 1 given theta 2 becomes the joint distribution of tilde of theta 1 comma theta 2. And then I can marginalize this because there is no theta 2 coming on the second term. This will actually give me, there will be no further integration, will give me pi of tilde of theta 1 times pi of tilde of theta 2 given tilde of theta 1, which is the joint distribution of tilde of theta 1, tilde of theta 2. So effectively I have proved this, you know, that pi is the invariant distribution of the transition kernel P that I wrote here. Here it states the detailed balance equation is satisfied, but as I mentioned before, the detailed balance or reversibility condition is a statement that guarantees this equation, but at least for the lecture today I can use the two concepts as meaning one and the same thing, and we will discuss the difference between those two later on. You can extrapolate that this equation being satisfied does not necessarily imply that the detailed balance equation is satisfied, but the detailed balance equation satisfied implies that this equation then is taken care of. So there is a little bit of small differences there, but right now pi is the invariant distribution of the transition kernel that you see in the equation on the top. So, I mentioned we need to satisfy this irreducibility condition and aperiodicity as well, and those things will actually ensure that this sample mean approximates the true expectation the way that we have seen with standard Monte Carlo methods, and of course asymptotically we will guarantee that the samples that we get from Gibbs sampling, they're actually samples that come from the target distribution pi. So let me give you one example of how irreducibility can create problems and effectively may not allow you to state, for example, that these samples will be samples coming from the target distribution pi. So let's consider that we have a distribution in two random variables, θ1 and θ2, that's the horizontal and vertical axis, and these red blocks are the blocks basically that have non-zero probability. So remember the Gibbs sampling, you start with θ2 and you sample θ1. So let's say that we sample θ1 in this region from 0 to 1. And now given θ1, we're going to sample θ2. So this will take us somewhere in this red block because here I have zero probability. So my θ2, let's say it's somewhere here. And now given that θ2, I will need to sample θ1. But because in this region the probability of θ1 is 0, I am going to remain, the θ1 is still going to be from 0 to 1. The idea here is that if you start taking samples starting with θ1 in the region 0 to 1, you will find yourself that the samples θ2 are going to be in this region from 0 to 1, and then the samples θ1 again are going to be in this region 0 to 1, and then θ2 again is going to be from 0 to 1, which means that you will never reach this block. So effectively this irreducibility condition that we discussed is not satisfied. So if you start, let's say, at any location in this red block, there is zero probability that you will actually transition to any state in the second red block. So in this case, we're not going to be able to prove what I had before, that these samples are actually coming from the target distribution pi. For sure this is not going to be the case. Now this is a little bit a weaker condition, so maybe you're lucky and this gives you a reasonable approximation of the expectation, but certainly you will not be able to converge to the true target distribution. Okay, let me give you another example now, since I mentioned this aperiodicity condition. Let's take a finite number of states. So let's say that the support state has discrete values 1 and 2, so we only have 2 states, and the probability from state 1 to 2 and from 2 to 1 is equal to 1. So if you're at state 1, you will transition with probability 100% to 2. If you're in 2, you will transition to state 1 with probability 100%. So you can appreciate that the limiting distribution of this transition kernel is P1 equal to P2 equal to 1/2. Now notice the following. Let's say that you start with a state x0 equal to 1. So at time 0, at iteration 0, you start at the state state 1. So at time or iteration 1, you're going to be in state 2, and then at time 2, you're going to be back to state 1, and at time 4, you're going to be back to state 1. So at time 2n, you will always be at state 1, and at time 2n plus 1, so an odd number, you will always be on state 2. So now you can see that this really don't represent the target distribution that says pi 1 equal to pi 2 equal to 1/2, because according to this, if you start at time 0 at iteration 0 at state 1, there is 100% probability that you're going to be on state 1, right, at times 2n. That probability is not 1/2, is 1. And so you can appreciate here that actually even though this averaging converges to the true expectation, xn is not distributed according to the target distribution that is given by pi 1 equal to pi 2 equal to 1/2. Okay, so we have seen the irreducibility condition. We talked a little bit about the a periodic condition with at least with some examples, and so we assume for now that the Gibbs sampling takes care of all of these mild assumptions, and so we proceed to give you how the algorithm is going to look like. So in general, if I have a vector that has p components, okay, so we did the case of p equal to 2 before. So if we have a vector with p components, you can start with some initial state that you see, and then you can start updating in sequence each of the parameters. And you notice the way that I wrote the conditional here. This is the conditional of theta k given all the other parameters, and all the other parameters are going to be fixed on their most updated values, which means the k minus 1 parameters have already been sampled and so have been updated. The other parameters from k plus 1 to p have not been updated, so I'm going to use their values at iteration I minus 1. So again, in the conditioning, use the most recent values that you have, and that will be the Gibbs sampling, where again, we sample, as you see in this algorithm, we sample in sequence. You can do this, a modification to this algorithm, where rather than sampling, let's say, parameter theta 1, then theta 2, then theta 3, you can sample arbitrarily some component k. Maybe k is selected from the uniform distribution from 1 to p, okay? And then you update a random component theta k, and that leads to what is called the random scan Gibbs sampling algorithm, and I'm going to give it to you here. It practically seems to me we're still actually this is the same algorithm as what I discussed before, so not what I was referring to. So what I was referring to is given hopefully on this slide, and here it is. So you sample the component k from a uniform distribution over these indices 1 to p, okay, and then you fix all the other parameters to their most recent values, and then you update only the component k. If you do this randomly, right, and you select randomly a component to update, this algorithm converges, and it is known as a random scan Gibbs sampler. Now, the probability of selecting here from the uniform distribution over the stage 1 to p, you can imagine the easiest way to do is to select the probability to be 1 over p, and I'm repeating this algorithm on this slide. So the probability that you sample, let's say, the parameter j that you will update the parameter j is given as 1 over p. All right, let's see some examples, and this example to demonstrate the Gibbs algorithm will be a bivariate Gaussian distribution. So I'm writing this with correlation coefficient rho. The marginal distributions are of course univariate Gaussians, so you anticipate that if the Gibbs sampling works well here, and you take the samples, let's say, only of x1 or x2, that effectively those samples should correspond to these marginal Gaussian distributions. So to implement the Gibbs sampling, we will need the conditionals. We already have seen this in multiple lectures in the earlier part of the course. The conditional distribution of x1 given x2 and x2 given x1 are given by these Gaussians. And again, pay attention, when you sample x2 given x1, you use the most updated value of x1 that comes from step 1. So if you use these conditional distributions and you take only your samples x1 and you create a histogram, you can see that directly takes you to the target marginal distribution that we saw in the previous slide. And on the right, you see the moves that you do in the x1, x2 plane, starting from some arbitrary location that's here taken as -3, 3. So you can see here you have very good mixing. You can go over most of the support space, okay, and this leads to rather nice results for the target distribution. Now, if you take the correlation coefficient to be very high, almost 1, and you start with the same initial state, you can see now the variables are highly correlated. You can see that you don't explore much of the stochastic space, okay, and you can see the histogram of a particular value, let's say of x1 here. It doesn't look to be following the target marginal distribution that I showed you a while ago. Okay, so this is when you have these highly correlated variables, this is what to anticipate using the Gibbs sampling. I think I'm repeating the same example with potentially different software. So again, this is samples from a bivariate Gaussian. I'm writing here without using the correlation coefficient in terms of the parameters A and B. I take here actually this in the covariance, I take the 1, 1 and 2, 2 components to be the same, and I'm also applying this to this particular example with values of A and B being 100 and 99, and you can see how the paths in the x1, x2 space look like, and this is your target, the contours of your target distribution. So in this particular case, the algorithm works quite well. You can see a similar implementation where now, instead of giving you the conditional distributions, I am writing them sort of like an autoregressive model, if you like. These equations are identical to the sampling from the conditional distributions I had before, so you can check that the formulas here are correct. The only thing I need to pay attention here is these coefficients that you see. So C inverse 1, 2, this is the 1, 2 component of C inverse. This is the 1, 1 component of C inverse, okay? So this is not, so just be sure, so this is not 1 over C1, 1, right? It is the 1, 1 component of C inverse. So for example, the 1, 1 component, you remember the C matrix before was A, B, B, A. So C inverse, the 1, 1 component would be, I can guess now, would be A divided by A squared minus B squared. Okay, so the inverse of that will be what you have here in the denominator. If you plug in those, you will see that you get exactly the same equations as what I had on the previous slide. I believe in some of these MATLAB programs, if they still work, they obviously were prepared with an earlier version of MATLAB, but you can see an animation of how the Gibbs sampling algorithm operates. The same thing here, so nothing new. And you can use the Gibbs sampling algorithm to sample from a mixture of two Gaussian distributions. This is what you see here. And now you can see how successful we are to actually move from one of the Gaussians to another. So we're not being trapped in one of the Gaussians, okay? So this is very important. And actually, you will see later on when we talk about the Metropolis-Hastings algorithms that does, implements Markov chains using small random walks. You will see if you try to use the Metropolis algorithm to do sampling on a Gaussian mixture, it doesn't work too much because you always get stuck to one of the modes. So what you do is, you integrate it in your transition kernel with a Gibbs sampling, because that will allow you once a while with Gibbs sampling to do big steps and move from one of these modes to another mode, explore that mode for a while and then come back to the first mode. So some integration of Gibbs sampling with all the algorithms in practice is quite effective. And here again, this is another implementation from sampling from a Gaussian mixture. Here is an example of using the Gibbs sampling to sample from a binomial distribution. All right. So the two conditional distributions in this case, the distribution of x1 given x2, of course, is also binomial, and the distribution of x2 given x1 is a beta distribution. So if you use for given parameters alpha and beta, and n equal to 20 in some initial state that here I take it arbitrarily as 0, 0. If you do this for many iterations, then if you use the samples x2 alone and you create a histogram, you can see that the samples give you a beta distribution, which actually turns out to be the target distribution for this particular example. Okay, so let me do an example that this comes from the Bayesian core textbook, which is a rather nice Bayesian example. So let's say that we have a likelihood model that follows the Cauchy distribution, where the parameter mu is an unknown. Okay, so we collect two measurements from the Cauchy distribution, x1 and x2. So the likelihood is, as a function of mu, is written like that. Okay, so this is my likelihood model. Now, what I am going to do is we're going to use a prior on mu that I take it to be a broad Gaussian, centered around 0 with a variance of 10. Okay. And the posterior is going to look like this. Now, I am going to ask, can I use Gibbs sampling to sample from this particular posterior? And of course, the answer is no, because Gibbs sampling makes sense, right, for high dimensional distributions where we use the conditionals to sample from. Here is a posterior distribution with only one parameter, which is mu, so it is obviously not clear on how this can be related to Gibbs sampling. It's not clear how Gibbs sampling can be used to sample from this distribution. Well, observe the following trick. All right, this is from Bayesian core. If you are good at calculus, each of these terms, 1 divided by 1 plus xi minus mu squared, for xi being either x1 or x2, is the integral from 0 to infinity of this function here that introduces these variables omega 1 and omega 2. All right, so in some sense, you can start looking now at this posterior distribution and think of it of representing a marginal of a three-dimensional distribution in the space of mu, omega 1, and omega 2. So now you can see how potentially Gibbs sampling is going to come to play a role. Of course, to be able to think of Gibbs sampling, we will need to know what the conditional of mu given omega 1, omega 2, and then the conditional of the omegas given mu. And so this is the, the joint posterior, if you like, of omega 1, omega 2, and mu, right? So this is again my likelihood model. This is my prior on mu, okay? And the conditionals, immediately you can see that are easy to write down, and actually they turn out, the conditional on mu, it turns out to be a Gaussian, and the condition for each of the omegas, it turns out to actually be an exponential distribution. You can immediately see this by looking in this joint distribution of mu, omega 1, and omega 2. So here is how the conditional of mu looks like. This is the conditional of omega looks like, and actually we're ready to do Gibbs sampling. And obviously you're going to have to sample omega 1 and omega 2 in the process that you don't really need, but you need that to be able to create samples of mu. These are the samples of mu in the last 100 iterations of the chain, and this is the histogram of mu t that corresponds to actually the target posterior distribution of interest. Now you notice the posterior here is bimodal, right? And if you actually zoom carefully on this last 100 iterations of the chain, you can observe that the chain mu t moves in real space. It alternates visiting basically each of the modes of the target posterior distribution, okay, from one step to another. So there's a very good mixing of the chain that allows us to go from one mode to another, and the histogram generated, it's very nice. And again, the only thing we had to do was to actually solve this problem in 3 dimensions, right? By introducing these dummy variables omega 1, omega 2, then we disregard omega 1 and omega 2, and we keep only the samples of mu that you see here, both the different paths of the mu's and then the histogram that generated the desired posterior distribution. Okay, so we have applied the Gibbs algorithm to update one component at a time. When you see in research programs the Gibbs sampling algorithm, it is not unusual to actually use block conditional. So rather than compute samples of one component at a time, you compute samples of a block of components at a time. So you can think, if you have a block A, you update all the variables of that block A given all the other variables, right? So this block Gibbs algorithm, it is used often in practice, and it makes sense to use some intuition to put variables that they are maybe more correlated together, all right? And so you may have to do some thinking as to how to actually arrange your variables so that the Gibbs sampling algorithm can be as effective as possible. I also mentioned combining the Gibbs sampling with the Metropolis algorithm that we will visit in a few lectures. So the Metropolis algorithm is based on a Markov chain that uses a random walk, right? So the steps usually taken are small. So integrating this with Gibbs allows you to use the merits of both algorithms, and this combination is known as the metropolized Gibbs algorithm, and it is used very often in practice. Okay. Now, before I move to say a few more things about the Gibbs algorithm, let me say that we mentioned that the transition kernel, right, needs to have as an invariant distribution the target distribution. And so how you choose the transition kernel, it requires a careful consideration. Gibbs sampling actually tells us explicitly what that transition kernel is in terms of the conditional distributions. But then we also had to satisfy this irreducibility and aperiodicity conditions. And at least for now, up to this point, I told you, let us not bother yet about those two conditions in the context of the Gibbs sampling. Okay, I gave you, of course, examples to tell you when you will get in trouble, but we really didn't bother to say anything in the context of the Gibbs sampling algorithm. So one of the things that I want to mention is, let's take this example that is not very much different from the one that we discussed earlier regarding the irreducibility of this Markov chains. So let's suppose that we have two variables, x1 and x2, and the non-zero support space, where the probability of x1, x2 is non-zero, are these two circles that you see here. So now you can appreciate that if you use the Gibbs sampling algorithm and you condition x1 to be in the region corresponding to this left circle, you will never be able to reach the circle on the upper right, okay? Because if you condition, so if you start, right, and you sample x1 given x2, so if let's say your x2 is, let's say we condition on x1 negative, okay, then the x2 that we will get will be negative, okay, and then if we use that x2 to compute x1, we will only get a negative x1, and again we will only stay on the circle on the lower left. Now, if you have a case like that and you want to use a Gibbs sampling, you may be able to do a coordinate transformation. Here is a coordinate transformation, define some new variables y1 and y2, and in that case, the support space of the variables y1 and y2 takes the form of these two circles. And you can see now that actually you have no difficulty to do Gibbs sampling for the variables y1 and y2. So let's say if y1 is in this region corresponding to the left circle, then y2 will be in the region that you see here, from minus 1.5 to 1.5. And then when you try for a given for a given y2, you try to sample y1, there is a non-zero probability that you may find yourself on the circle to the right, and then from there is a non-zero probability that you will be on the circle to the left. So the idea here is a careful selection of the variables may allow you to actually use the Gibbs sampling effectively without having to worry about these irreducibility issues that we have seen in this example. Okay, so the general recommendations are use this block Gibbs algorithm that I do not elaborate a lot, but usually block variables that they are more correlated together, so put them together, and try if you have a very high dimensional density that you need to sample from, obviously see if you need to sample in those high dimensions. If you don't need certain variables, if they're latent variables, maybe try to see if you can actually integrate them out, so that way you can get a lower dimensionality problem. And of course, if you can reparameterize, if you can change maybe your space to a space of some new variables, maybe issues similar to the ones that we talked about irreducibility before can be addressed. So, but again, the idea of Gibbs sampling is very powerful, and used in combination with other algorithms very often in Monte Carlo methods. Okay, so let me move to our last example for today. That is to use Gibbs sampling to do Bayesian variable selection. This topic is so important that I will actually devote a whole lecture in fine detail following a chapter from the Bayesian core textbook. But right now I'm going to give you a high-level presentation on how Gibbs sampling can be used in the context of Bayesian variable selection. So we are assuming we have a linear regression model. Betas are the regression parameters, and my problem is p-dimensional problem. So I have these inputs x1 to xp, and I have some Gaussian noise. Okay, so in a Bayesian setting, you need to put some, prior on the beta, and you need some prior on the noise sigma. So usually the typical prior that we have seen in our earlier lectures for the variance would be an inverse gamma distribution, and regarding the parameters beta, you can actually use a Gaussian model, or as it is shown on this equation that you see here, a mixture of two Gaussians. So let me elaborate a little bit. This we have seen it, so there is a hyperparameter here, delta square, okay? And I have another component that involves this parameter alpha, and as indicated here, alpha is a very small number. So why do I actually need to have, or I think I may need to have this component, this Gaussian component here, because you notice if alpha goes to 0, then if beta is sampled from this Gaussian component, then the corresponding beta k is going to be 0, as alpha is very small, okay? And if beta k is very 0, that's immediate, tells me that the xk covariate or input variable is not needed in my regression model. So that's what variable selection is, okay? So by having this mixture, potentially we may be able to have, to model properly the variables that need to be in the model to explain the data, and also we may be able to get rid of the betas that somehow are relating to the variables xk that don't seem to affect, they're not needed to interpret the data. So what we do is we use a Gaussian mixture like that with alpha being a small number. And the way that you implement a Gaussian mixture is you're going to need a latent variable gamma k that takes values 0 and 1. And obviously you can appreciate that if gamma k equal to 0, then beta k is sampled from this Gaussian. If gamma k is equal to 1, beta k is sampled from that Gaussian. And you're going to need to put some priors on these gamma k values. And not knowing any better, you assign probability 1/2 to gamma k being equal to 0, and probability 1/2 to gamma k being equal to 1. Now, what you see on the slide is a potential, right? A potential way to implement a variable selection, because it allows you, if somehow gamma k is equal to 0, right, then your beta will be selected from this Gaussian, and as alpha goes to 0, then the beta k will be equal to 0, which means the xk will not be anymore in your model. Okay, so the question is, will this work? All right, so let's try to see if for this particular model Gibbs sampling can be applied. So to apply Gibbs sampling, we will need to compute the conditional posterior distributions of all my parameters, and all my parameters involve the betas. Now they involve these gammas that tell me which parameter is in the model and which one is out, and of course it's going to involve the noise sigma squared. Okay, so And so we're going to need to compute the conditional of beta, that's a Gaussian, the conditional posterior of sigma square, which is an inverse gamma, and we're going to compute this posterior of the gamma parameters. Okay. Now let me show you I'm not going to discuss yet on how we're going to compute this posterior of gammas. I'm going to give you some insights shortly, but let me do the following thing. I'm going to write down, using Bayes' rule, the posterior of gamma k given the parameters beta k and sigma square. Okay? And actually, so what I have here is I have the probability of gamma k equal to 1 given beta k and sigma square. So you can write this as the probability of beta k given gamma k equal to 1, which is, if you remember, is this Gaussian, and then times the probability of gamma k equal to 1, that's 1/2, divided by the sum that you see here. Okay? So actually what I have here, I don't even have the posterior, right? I'm writing this using using my prior model, right? That this is what I had before. Okay? So look what is going to happen looking at this probability of gamma k equal to 1 given my betas and my sigma square. As alpha goes to 0, this fraction here will go to infinity. So e to the minus infinity will give me 0, and then this thing and this thing cancel, which means the probability of gamma k equal to 1 given the betas and the sigma square is equal to 1. So effectively, the model will never be able to explore variables not being part of the model, because it will assign probability 1 to all the variables being in the model. Okay? So effectively, I will not be able to use this in the context of Gibbs sampling, because the system will be reducible. Okay? And I demonstrate this in the context of the prior distribution, but basically you will get the same result when you compute the posteriors of the parameters gamma k equal to 1 and gamma k equal to 0. Okay? Now, in this particular case, the way that I wrote the posterior for all these gamma k's to be independent, and I will briefly mention how these posteriors are being computed, but on a model at least that we know has some chance of working, because this particular model is actually not going to work, because as alpha goes to 0, it is reducible. So this Gibbs sampling approach in this particular model is not going to work. So the starting assumption that I indicated here, using this Gaussian mixture to define the parameters beta k, or even better, these equations from the top conditioning beta k on gamma k equals 0 or gamma k equal to 1, will not give me the irreducibility condition, so I'm going to get in trouble. Now, another possibility would be to modify the algorithm in the following form. So we will still consider alpha to be close to 0, but now you notice instead of having beta k xk, I am going to have summation of gamma k beta k xk plus my Gaussian noise, and this is going to be such that gamma k is going to be 1 if the xk input variable is included, and gamma k equal to 0 if the xk variable is not included. Notice, however, because I have the gamma k's and the beta k's both in my regression model, I am going to have to include this parameters beta k regardless if gamma k equal to 0 or equal to 1. So obviously that doesn't make a lot of sense. So this particular model doesn't seem to be a sensitive model to use to implement Gibbs sampling for variable selection. So what is left? Here is the correct way of doing this. we're going to write the regression model as summation of beta k xk plus Gaussian noise, but we're only going to include the parameters x, the input variables x, and the parameters beta gamma for the input dimensions that are included in the model, and I denote this as gamma k equal to 1 variables. Right, so the summation that you see here includes only the case for which gamma k equal to 1. So that means in my original model that I had summation over all k's of beta k xk, now I only have to use a subset of the beta gamma parameters and the x gamma input variables that they're such that gamma k equal to 1. Okay, so think again of x gamma representing a subset of your input variables, and beta gamma would be the corresponding parameters to that. And again, gamma is defined, by, I'm going to give it to you explicitly. Gamma is, I assign gamma exactly as before to each of my input variables, and I define x gamma to be the subset of all the x's including xk for which gamma k equal to 1. And similarly, beta gamma is the subset of all the betas that includes only the betas for which gamma k is equal to 1. So obviously here the number of parameters would be the summation of these gamma k's, because lots of these gamma k's are going to be 0, not included in the model, and gamma is going to be less than p. So with this notation for beta gamma and x gamma, you can appreciate that if you knew what gamma is, this is your standard regression model. By the way that I write here, right? This beta and x are vectors, okay? So, but the way that I have it here is like a standard regression model, but instead of having a vector beta and the input variable x or the design matrix x, I have beta gamma and x gamma, okay? So we're going to need some prior distributions. The prior distributions will be, our standard prior for beta and sigma squared that we have seen in earlier lectures. So this will be a normal inverse gamma. So given sigma squared, beta gamma follows a Gaussian, and I use a hyperparameter here, delta squared. And this matrix is the identity matrix of dimensions n gamma by n gamma. And sigma squared follows an inverse gamma distribution. This is the chi-squared distribution, right, that we have seen earlier in the lectures. Now for a prior on gamma, we're going to take 1 over 2 to a power p. Remember, I have p variables. Each of these variables can be on or off. So the probability of being on or off is 1/2. I have p of those variables. So for a given values of the components of gamma, the probability is 1 over 2p, where I assign again equal probability for a given variable k to be in the model and not to be in the model. Okay, so we're going to need to produce the posterior of the gammas. Now the beta gammas and the sigma squared given my data set D, and I write this posterior as the posterior of the conditional of beta gamma and sigma squared given gamma times the marginal posterior of gamma. Okay, I will elaborate on a second on what this is. Okay, so the marginal posterior of gamma is the marginal likelihood. Notice there is no beta or sigma squared here, so this is the marginal likelihood times the prior on gamma that we saw it before is 1 over 2 to the power p. Okay, so I now what I need to do is I need to compute this posterior, and I need to compute this marginal posterior of gamma. Okay, so let me just give you directly what this marginal likelihood is. Okay, so you remember the way we calculate the marginal likelihood. It will you can write this as the likelihood of D given the parameters beta, gamma, and sigma squared and gamma times the prior beta, gamma, and sigma squared. And when you do the integration in beta, gamma, and sigma squared, you get this very nice expression that we have seen in our regression lectures. So this is the marginal if I knew the parameters gamma. And you notice these equations are the same as the ones we have seen for our regression model, where I throw this subscript gamma that basically collects only the parameters and the inputs that are correspond to variables that they are in the model, and that is defined by that vector gamma. So once I know gamma, that defines all of these subsets of variables and matrices and vectors that you see here, mu gamma, sigma gamma, etc. And this is the details for what mu gamma is and sigma gamma. So I do have this marginal, the marginal likelihood. I do have the prior, and I have produced this marginal posterior of the parameters gamma. Okay. Now, eventually, we're going to be able to. We will need to compute the marginal of each of the gamma parameters. But if you think about it, because each of the gamma k variables takes the value 1 or 0, effectively, the way that I'm going to compute the marginal, let's say, of gamma k given all the other gamma variables, what I can do is I can use this distribution, right? Because those marginals will be proportional to this distribution, and simply go and evaluate this distribution using these equations for gamma k equal to 1 and gamma k equal to 0. Okay? Again, for Gibbs sampling, I am going to have to update the probability of gamma k given all the other gammas, all right? But that probability is proportional to this p of gamma given d, all right? And so the only thing you will need to do is evaluate of this by taking explicitly gamma k equal to 1 and gamma k equal to 0 and all the other gammas to whatever values you already have evaluated, and that will fit nicely in the context of the Gibbs sampling algorithm. Now, the posterior for beta gamma and sigma square is again a normal inverse gamma distribution. We have seen these derivations before. If I knew gamma, you can cut and paste the formulas from standard regression that we have seen in the earlier lectures, and this is what I have here. And so I'm going to start showing you how this algorithm is going to work. But let me just say that if you want to experiment with priors for gamma that they are not the uniform priors, you can actually assume that each of the gamma i's is given from a beta distribution with parameter lambda coming from the uniform distribution. You can assume a hierarchical Bayes model where gamma I comes from a beta distribution, each of them having its own hyperparameter lambda I, but all of them linked together because these lambda i's are samples from a beta distribution with parameters A and B. So you can do lots of fancy things if you wish, but and also when we discuss about regression models, if you remember, the conditional of beta given sigma square was a G prior. This was the Zellner G prior. So instead of having the identity matrix, you can actually have this X gamma transpose X gamma inverse. It will only require minor modification of your results to actually get this to work. And you can even take this parameter delta that you see here, and rather than fixing it to a constant value, you can actually make this to be given by some inverse gamma distribution with given, so this is G square distribution with given parameters A0 and beta 0. So again, you can take various variants of the priors that you use for this Bayesian regression model. All right, so let me give you the algorithm. First, I'm going to assume that the parameter delta that we use in our prior model for beta given gamma is constant. All right, so here's how the algorithm is going to work. You start with some values of the vector gamma 0. So you decide, maybe you keep all the parameters in your model. All right, so that's your gamma 0 being 1, 1, 1, all the way up to the p component. Then you start the Gibbs sampling algorithm. You're going to sample and update at iteration I gamma k, and maybe you will update each of these components one at a time. And so you will need to have this conditional posterior of gamma k given all the other gammas. And as I mentioned to you, the way to actually evaluate this, an easy way, will be this conditional distribution is proportional to the posterior of gamma given your data d. So really what you need to do is take the posterior of gamma and go and evaluate, gamma k can only take the values 1 and 0. So evaluate those two probabilities effectively. So this step will be equivalent to evaluate the probability for gamma k equal 1 and gamma k being equal to 0. Again, remember all the other parameters. In this case, this is a marginal posterior, so it only involves gamma, but all the parameters that you already have updated need to have their most recent values. The rest, they can have their values at the previous iteration. Now, once you update all of this, or within the loop, the way that it is shown here, you can actually come and update the parameters beta gamma and sigma square, right? And you can sample those with given gamma I, you can use the posterior of beta gamma and sigma square, and you can use another loop, with Gibbs sampling in between here. And if you want, you can update the parameters beta gamma and sigma square. I call this an optional step because you notice to update gamma, the only thing that I need is the marginal posterior, so that doesn't involve beta and sigma square, so I don't really need to update beta and sigma square because beta and sigma square have been integrated out in this posterior that you see here. So again, this is Gibbs sampling with delta square being known, and you can apply Gibbs sampling when delta square is also updated. So the only thing that is new here is there is a dependence of this marginal posterior on delta square, and then obviously you're going to have to update this delta square, so you're going to need to use the posterior of delta square given your parameters beta gamma. Okay, now again you notice I use the marginal posterior of the gamma parameter, so there was not conditioning on beta and sigma square, so this is a little bit different from what we usually do with Gibbs sampling, but it turns out that actually doing so, the Gibbs sampling that you get is way much more efficient than if you were conditioning gamma on the parameters beta and sigma square. Okay, so now the algorithm, obviously it works, but if you try to run this algorithm, you will realize that it is very slow. It mixes very slowly. So if you try to run this in your PC, and you will find out that it may take a few hours to actually converge and find you the best parameters that need to remain in the model to explain your data set. So there is a table that I'm going to provide you. I cut and pasted this table from this reference, but a lot of the results that you see here seem the numbers to be cut and paste results from the Bayesian core book on the corresponding chapter on Bayesian regression variable selection. Okay, so let me just go through what you see here. The first column corresponds to ridge regression with given delta squared, okay, and it gives you the most the highest ranked models when it comes to the probability of P of gamma given the data. So you can see the model 0, 1, 2, 4, 5 is the most relevant model. 0, by the way, corresponds to your bias term that has to remain in all the other models. And you can see now variable 1, 2, 4, and 5 are in this model. And this probability is 0.1946. The second model that involves also the variable 9 has a much less probability, which is 0.0321. The second column corresponds to Zellner's G prior with a parameter delta squared being fixed. Again, the corresponding probability for the model 0, 1, 2, 4, 5 is 0.2316, okay? And the last column corresponds to the case where we use the Zellner G prior, but now delta square is being estimated, and again the highest rank model is given by these numbers. Now I am extrapolating, looking at these numbers and comparing nodes with what is given at the Bayesian core book, that these numbers that you see here have not been evaluated with the Gibbs sampling, but have been evaluated exactly. So basically you do an exhaustive search over all possible models, right, by keeping each variable on or off, and then it turns out that this combination of variables being on gives you the best model. Now, if you implement the Gibbs sampling for these algorithms, basically the answers will not be exactly these numbers, but will be very close to these numbers. Okay, I am going to try to review the details of these calculations in a separate lecture simply for the history books, because this is an extremely important problem. So I'm going to come back to show you these numbers and compare the actual evaluations of this posterior versus the evaluations coming from Monte Carlo sampling, okay? And you will see that the numbers that we will obtain for the most probable models will be similar to what you see on this table. All right, so that's Gibbs sampling, a long lecture today. We introduced Gibbs sampling and we introduced Markov chain Monte Carlo. We talk about the transition kernels and their limiting distribution. We wrote down the transition kernel for Gibbs for the Gibbs sampler, and we talked about the conditions of irreducibility and aperiodicity. So there is a lot of information that you need to understand from the lecture today, but some of these concepts again will be repeated when we discuss the Metropolis Hastings algorithm. So this is all for today, and I will be back with another lecture in 2 days. Thank you.